Hi, I'm Winter Broussard, and I'm presenting my research searching for trends in the atmospheres of exoplanets. The first measurement of an exoplanet's atmosphere came in 2001, when Charbonneau et al. Made a detection of sodium in the atmosphere of HD 209458b. This detection was made using the technique of transmission spectroscopy. When an exoplanet is transiting its host star, stellar radiation can pass through the opaque upper atmosphere of the exoplanet. Depending on the composition of that upper atmosphere, different wavelengths of light will be blocked. When a particular wavelength of light is absorbed, it's not going to reach our telescopes on Earth. Thus, at the wavelength where light is being absorbed, the radius of the planet will appear larger. If we measure the spectra of the star while the planet is being eclipsed and compare it with the spectra of the star and planet combination, the difference in these two spectra will be the planet's spectra. So we get a transmission spectrum like this, which changes as a function of Rp to R star, or the radius of the planet to the radius of the star. The red line is showing the best fit atmospheric model, with the blue shading zones indicating different confidence regions. Looking at this elevated point here, labeled Na for sodium, this point is elevated because at the wavelength where sodium is observed, the radius of the planet appears larger. This exoplanet's atmosphere is blocking more light at the wavelength where sodium is being absorbed. This means that sodium is present. Many planets have had their atmospheres characterized with transmission spectroscopy at this point. Despite this, very few studies have been conducted with the aim of determining if there exist any trends relating exoplanet atmospheric compositions to their physical parameters, their radius, their temperature, orbital period, etc. This is the objective of our search. Hot Jupiters are particularly good for transmission spectroscopy. These are planets that are as big as Jupiter, but unlike Jupiter, they have very short orbital periods and have very high temperatures as a result. You can see here the orbit of the hot Jupiter HD 189733b, which is one of the hot Jupiters in our search. HD 189733b orbits well within the orbit of Mercury, taking only about 2.3 days to fully orbit its host star. Hot Jupiters are good for transmission spectroscopy because their hot temperatures lead them to having very puffy upper atmospheres, meaning a lot of stellar flux can pass through during transit. The more stellar flux that can pass through, the deeper the features of the transmission spectrum can be, and the more likely it is that we'll be able to characterize the planet's atmosphere. Thus, we have started our search with hot Jupiters because they are great for transmission spectroscopy, and we expected that there would be enough data when looking at this parameter space in order to characterize trends. I'll explain this plot more in a moment, but it's showing the planets we've included in our search in the red box. These are planets with periods of up to 3.5 Earth days and with radii between 1 and 2 times the radius of Jupiter. The Habitable Zone Gallery is a website created by our collaborators, Dr. Stephen Kane and Dr. Don Gelino. The Habitable Zone Gallery gathers the names and physical parameters of confirmed exoplanets from the NASA Exoplanet Data Archive and makes several calculations, including the equilibrium temperatures of the planets and the extent of the habitable zone around each star. For the purpose of our research, we are interested in the temperature, radius, density, orbital period, and mass of the planets. To accomplish this, we utilize a Python script, which takes data from the Habitable Zone Gallery and returns the names and physical information of the planets within a desired parameter space. The result of running this code is the plot you see here, which contains a point for every planet in the Habitable Zone Gallery with both period and radius data. As previously stated, the planets within the red box are the ones we are interested in. Planets with periods of up to 3.5 Earth days and with radii between 1 and 2 times the radius of Jupiter. There are 191 planets in that red box. We conducted a literature search for each of those 191 planets and found that 27 had previously published papers. Of those 27, 24 had published transmission spectra in the overlapping wavelength range of 3,000 to 9,000 angstrom. These 24 are colored blue in the plot. We have chosen to use this wavelength range because a number of features are present here, including sodium and potassium. By reviewing these papers, we determined that 9 of the 24 had definite or potential absorption of sodium and/or potassium. To search for trends, we created plots for each combination of parameters. Here, I'm showing a plot of the mass versus temperature values of the 24 planets. The legend down here indicates which planet corresponds to each point. Planets which show definite potassium absorption are indicated with a solid green circle, potential potassium absorption with a dashed green circle. Planets which show definite sodium absorption are indicated with a solid blue circle, potential sodium with a dashed blue circle. We made 10 plots in total, showing each combination of parameters. Here are 4 of the other plots, and 4 more, none of which show any indication of a trend. So, we have found no trends relating the presence of sodium or potassium to an exoplanet's physical parameters. To quantitatively say this, we have conducted the one-dimensional Kolmogorov-Smirnov test to test if the distribution of planets which show absorption is the same as the distribution of planets which have not been determined to show absorption, to see if these two populations are different in a statistically significant way. By conducting this test for each parameter, we found no statistical difference between the two populations. The resulting p-values, or probabilities, that the two samples came from the same parent population was always greater than 0.37. For statistical significance, we would need to see a p-value of less than 0.03. Exemplifying this is the histogram you see here, which shows that the distributions of masses for planets with sodium or potassium absorption is the same as the distribution of masses of all the planets in our search. So we found no statistical difference between planets which have been found to show absorption and planets which have not been found to show absorption in one dimension. Having found no trends relating potassium and sodium absorption to a single parameter, trends relating potassium and sodium absorption to combinations of parameters were investigated. This can be accomplished qualitatively by plotting each combination of parameters, as shown previously. But in order to have the same quantitative results as for single parameter trends, we investigated methods of adapting the KS test so that it could be utilized to conduct a two-dimensional test. For a while, we didn't think this would be possible, as the KS test normally only works with single parameters. Luckily, we discovered a code on GitHub which would allow us to utilize the test with 2 samples, testing the statistical difference between combinations of parameters for those 2 samples. To use this code, we were able to create 4 lists. X1, which represented the first parameter in the first sample and contained a list of the values of that parameter for each of the planets in the first sample. Y1, which represented the second parameter in the first sample and contained a list of the values of that parameter for each of the planets in the first sample. X2, which represented the first parameter in the second sample and contained a list of the values of that parameter for each of the planets in the second sample. And finally, Y2, which represented the second parameter in the second sample and contained a list of the values of that parameter for each of the planets in the second sample. For example, when conducting this test for radius and period, X1 was a list of the radius values of all the 24 planets. Y1 was then the period values of the 24 planets. X2 represented the radius values of the 9 planets with absorption. And Y2 represented the period values of the 9 planets with absorption. By conducting this test, we found a p-value of 0.766, so definitely no trend there. We conducted this test for each combination of parameters and found no statistical difference between the coupled parameters of the 2 samples. So we found no trends relating combinations of parameters to the presence of sodium or potassium in an exoplanet's atmosphere. For future work, we are planning to expand our parameter space of interest to include more planets in addition to expanding our wavelength range of interest to include absorption due to water. I'd like to acknowledge the scholarship support provided by the Mary Gates Endowment for this research. I'd also like to thank Dr. Dundon for her assistance with the statistical analysis, and Dr. Rodriguez Hidalgo and the other members of this research group.